Welcome to all. It's my pleasure to introduce the last but not the least of our invited speakers. Masahide Sasaki. I had the pleasure of attending QCrypt a year ago. QCrypt is the annual conference on quantum cryptography, and he was a keynote speaker at QCrypt in Singapore last year. And I was so dazzled by his talk that I wanted to have an encore, and that's why I selfishly invited him to talk to us about towards quantum photonic network.
Okay, thank you, Jill, for your kind introduction. And I also thank the organizers for inviting me to be here. My name is Masahide Sasaki, working at NICT. And it is my great honor to deliver an invited talk in this long-established conference of EQIS. The title of this talk is Toward Quantum Photonic Network, and the idea is to merge photonic and quantum networks. So photonic network is a broadband optical infrastructure to realize high capacity and low power communications. Quantum communication is to enhance photonic network in two directions. One is to capacity enhancement by quantum communication to realize maximum capacity and minimum power communication. And the second is the security enhancement by quantum cryptography. So it is to provide the provable security. And these two quantum schemes have been studied separately so far. And we want to combine it, and a unified scheme will be realized in the photonic network infrastructure. A new network paradigm realized this way may be referred to as quantum photonic network. And it is to realize maximum capacity and minimum power communications with provable security. So the measure is a secrecy capacity under a power constraint or bandwidth constraint. Okay? So in the following, I'd like to explain what is a photonic network and review current status and issues of quantum communications and quantum cryptography, and then discuss how to realize quantum photonic network. Okay, photonic network is an emerging infrastructure of optical communications. So it consists all optical node instead of conventional node of electrical processing, and it is to utilize broad band of optical fields and to resolve the speed limit and heating of electrical devices. Now, broadband optical transmission is realized by wavelength division multiplexing, and networking and routing is made by all optical processing based on wavelength switching. In this way, the transparency of optical link will extend over longer distance, and actually this optical transparency is the prerequisite for quantum cryptography as well. Okay, quantum cryptography can provide a means to realize the provable security based on photon transmission. So let's first see the security issues. Now, today's software-based cryptography is implemented by computer algorithms in the third or upper layers in the current network, and it is based on algorithmic security with the computational complexity. So it is not provably secure. It can always be threatened by emerging technologies such as high-power quantum computer. But more importantly, insisting on this sort of technology means that relying on electrical processing, and which is not compatible with the photonic convergence. So our concern here is a provable security which is compatible with the photonic network. The provable security is more or less based upon the analysis of the physical properties of a channel. So given a channel model, then the security proofs are made by showing the existence of code, error-correcting code, that can effectively establish the statistical independence between the legitimate users and the eavesdropper. So provably secure cryptography is also referred to as physical layer cryptography, and provable security is also called the information theoretic security. And quantum cryptography is an ultimate manifestation of the physical layer cryptography, and it consists of a quantum key distribution and one-time pad. And this QKD can offer a means to deliver key materials for one-time pad over an optical network. Okay? And this QKD is implemented in the bottom layer, in the physical layer. And once the secure keys are generated, then those secure keys can be stored at the upper layers and can be used for a variety of applications. And the combination of QKD and one-time pad can realize the provable security against an eavesdropper with the unbounded ability. So this is called the unconditional security. And QKD is also compatible with the photonic convergence. And as I said, the optical transparency in the physical network is a prerequisite for establishing secure quantum link. And QKD has been commercialized right now. And there are many novel QKD networks in the world, and many new projects are going on. However, wider adoption of QKD is not enough at all. So this is a really rough diagram, security versus the usability. Usability means speed, distance, inverse of cost, and so on. And the QKD is in a higher security side, and photonic network is the wider usability side. And there is a huge gap between these two. Okay? So QKD can realize the unconditional security in principle. In practice, however, QKDs suffer from side channel attacks, just like the all existing crypto technologies, and distance and speed are still limited. To combat these problems, there are several proposals and techniques developed, including the device-independent QKD to suppress the side channel attack effect and a quantum repeater to extend the distance. However, this gap, okay, this gap cannot be filled merely by improving this QKD technology itself. So I'd like to rearrange the diagram in the following way. So device-independent QKD is at the highest security side, and quantum repeater will extend the distance. And QKD first generation is now in practical use for unconditional security. And photonic network is the main infrastructure at the present. But its security is based on algorithmic security. So now I'd like to put a kind of new topic, which is the physical layer cryptography. So we make a compromise for the assumption for the range of security threat and to widen the usability, preserving the provable security. So this is a physical layer cryptography, and quantum photonic network means a integration of all these technologies. So in the following, I present the two topics, the QKD first generation and our new theory of physical layer cryptography. And so we start with our presentation about our recent stable operation of QKD, and then present a new scheme to extend the distance. It's a quantum relay. And then move on to a theory of physical layer cryptography, and we present how to characterize the secrecy capacity and how to quantify the trade-off between the reliability and security. Okay? So we start with the QKD. Now we are developing a gigahertz clocked WDM QKD. So it's a decoy state BB84 system. And this is Alice. It's a 19-inch rack, so this height. And Bob has a two 19-inch racks. And we can implement a totally 8 wavelengths multiplexing. And these systems are put to field test. The fibers are 22 kilometer field line in the loopback configuration. And 90% of these lines are in area over poles. So the fibers are directly influenced by various disturbances. So this shows how fibers are changing. So this is a nighttime, daytime, and nighttime, and we measure polarization drift. So this blue and black lines are polarization drift. Red dots are the atmospheric temperature, and this purple dot is the sunlight time. So you can see that the sunlight time directly affects the polarization drift. So the deviations are really stringent, and even under such severe condition, we have to stabilize the QKD operation. So we have developed a various stabilization technique. So this scheme shows our WDM QKD. So totally 8 laser diodes emit light, and then this light pulse are converted into Appel pulses, the time beam format, by this asymmetric Mach-Zehnder interferometer, and then these modulators put key data and decoy state information. Now, this is the photo of the asymmetric interferometer. It's a planar light wave circuit, and this is a long arm, and by carefully tuning the temperature of this part, then polarization state can interfere properly at output port right here. So in our system, polarization drift is not a matter, and we can stabilize the operation, but we further implement the feedback control of important parameters, such as the temperature of this planar light wave circuit, bias voltage for those modulators, and gating time for this avalanche photodiode. And we use a photon counting rate and bit error rate. So this is the recent QKD data. This shows a uninterrupted continuous QKD operation over 30 days. And quantum bit error rate is very small. It's less than 2%, which is really nice. And the secure key is 150 kbps for first channel and 80 kbps for the second channel. And let me compare our result with the recent field experiment. So the Swiss quantum marked the longest record of operation, which is about a year. And our work is the second longest, it's 30 days. But thanks to this high-speed QKD operation, we could accumulate a large secure key. It's 600 gigabits. So this is an order of magnitude greater than those in the previous works. And then to quantify the quality of long-term QKD operation, we introduce a new measure. It's a channel loss normalized secure key, and our result is 10 terabits. Now, using this quantity, one can estimate how large secure key can reliably be distributed for a given channel by multiplying this quantity by a real channel loss. So I suggest we use this sort of new figures in our future field experiment. Okay, this is the QKD, the current status of QKD. So we move on to the next issue. It's a quantum relay. Now, QKD network is currently made by classical capsule relay via the trusted node. Okay, it's so inside the node, we do not use quantum cryptography, just capsuling the key each other. But we would like to remove this trusted node assumption eventually. And quantum repeater can do it, but it is still immature. So I'd like to propose a kind of intermediate scheme. This is a quantum relay. Now, this quantum relay do not require any complicated entanglement purification, but the difficulty is imposed on the state preparation. So we have to prepare a large cat state. So our task is to establish a secure quantum link assisted by a quantum cat state. So there are 3 requirements. Coherent state as the signal carrier, entanglement for preventing universe dropping, and amplification process to beat the distance limit. So why to use coherent state is because coherent state encoding achieves the bosonic channel capacity. So this must be compatible with the photonic network. So the scheme to meet these criteria can be obtained by slightly modifying the quantum noiseless amplifier, okay, by simply replacing the single photon ancilla with the cat state. So let me show the schematic here. So receiver first prepares a superposition state of two waves of 0 and 1. So this is a cat state. Then this state is beam split into two beams, B and C, and the beam C is sent to the sender. And the sender have optical signals as input and combine it with the beam C. And Alice measured a single photon detection on those beam A and C. And by filtering outputs by specific photon detection signal, then Bob can realize the noiseless amplification like this to this classical inputs. Okay? Now the key mechanism of this scheme is a simple fact that the coherent state is the eigenstate of the annihilation operator. So due to this fact, entanglement can be created simply by beam splitting a cat state. Okay? So we have a cat state and then beam splitting, then we have a entangled cat state like this, and this can be used for teleportation. So now let me show a schematic again with some mathematics. Now the odd parity cat is beam split for a resource entanglement, and input is an arbitrary superposition of coherent state. So it's a cat state qubit, and this cat state qubit is teleamplified like this with the gain G. Okay? The gain G is determined by the reflectance of these two beam splitters. And beta is the amplitude of the resource cat and should be determined according to this relation. Okay? Now, unfortunately, this teleportation of this arbitrary superposition is vulnerable to losses. It's really, weak for all loss. So, but unfortunately, if the input state are restricted to the classical component like alpha or minus alpha, but unknown, either of which, then the effect of channel loss does not appear. Why? Because the coherent state is an eigenstate of the annihilation operator, and we can realize a noiseless amplification like this. So this can realize a loss-tolerant quantum relay. And we demonstrate this protocol in the laboratory. So let me briefly show the experimental result. So the upper panel is the input. It's a Wigner function and contour plot. This is a coherent state, and this is the teleamplified coherent state. Now the gain is 0.5, so this is the de-amplification. Okay? Then we increase the gain gradually, and this is a unit gain. It's just a teleportation, and then we further increase the gain, okay, and arrive at the maximum gain in our experiment. And the fidelity is 90% or higher for all the cases. But this is a lossless case. So in our next experiment, we add the 80% of channel loss and did the same experiment. This is a result. And we retuning the beam splitter reflectance of the Alice's beam splitter and almost realize the same result as the zero loss case. So let's compare. This is a lossless case, and this is a lossy case, and get almost the same result. So this demonstrates the loss-tolerant quantum relay, but this is only for binary coherent state. So next we consider application to BB84. Okay, so we have to extend our scheme to the 4 coherent states. So we use a 4-phase shift keyed coherent state, and this real component constitute X basis, and this imaginary component constitute Y basis. And we add common reference pulses, and pair of pulses carry the BB84 basis information. So this protocol is proposed by Rowe and Preskill. Now we introduce a relay node here and teleamplify unattenuated signals to the terminal node. Okay? So accordingly, we have to prepare a 4-component cat state like this, and this is beam split and used for resource entanglement. And Alice's measurement should be 4-port interferometric measurement, and conditioned on the click patterns like 0, 1, 1, 1, then we can teleamplify the 4 unknown input state to this teleamplified output state. So this is still in theory, and we'd like to present our simulation for future performance. So we compare 2 cases. One is direct transmission over the distance L, and the other is the teleamplified BB84. So relay node is put at a distance of x times L from the sender. So we compare these 2 cases. So here shows the key generation probability as a function of the distance. The stashed and dotted curve is for the original BB84 without any amplification. Then the 70 kilometer is kind of a distance limit. And these color solid lines are for teleamplified BB84. So you can see that we can remove the distance limit if we can generate a large enough cat state. And the size of the cat state should be determined according to this relation and plotted in this view graph as a function of the distance. So these areas are really reasonable. Now we can realize in the laboratory currently, but these curves are quite hard to reach at the moment. And to be more comprehensive, we add the cat size in the key generation performance. So to reach 100 kilometers, we need a cat state with 0.6 photons on average. And this is a small cat, and we can routinely generate such sort of a cat. So we are just ready for field experiment. And to go beyond the 200 kilometers, we need a cat state with 10 photons. So this might be a reasonable next challenge in the laboratory. Now to reach 300 kilometers, we need a big cat. It's 1,000 photons. So I have no idea how to do it. But anyway, this cat-assisted quantum relay might be useful to make a quantum space, quantum linking space. So we launch the large cat state, and quantum cat go to space. So we assume a kind of satellite at the low Earth orbit, which is about 700 to 800 kilometers in altitude. Then air loss is 30 dB, and the typical system loss is 15 dB. So the total loss is something like 50 dB. And this loss corresponds to 250 kilometer telecom fiber. Now this performance is something around here. Okay, so suppose we can generate a cat state with 10 to 100 photons with a 100 gigahertz repetition rate, then the final secure key rate would be 10 to 100 BPS between low Earth orbit satellite and the ground. So you might think this key rate may be still poor, but this is the best value that can be achieved in the near future technology. Okay? But I think it's still poor, so I'd like to consider a kind of new physical layer cryptography which can also pass through high capacity, preserving the provable security. But to discuss these issues, I have to review some basic concept of the capacity. Okay? So let's study the capacity issue first, the channel capacity. So it is how to transmit as much information as possible faithfully through a noisy and lossy channel. And error-free transmission is possible even when the channel is noisy. So we add redundancy. So suppose we want to send 16 kinds of alphabet. Okay? Then 4-bit strings of 0 and 1s are enough to represent all 16 messages. However, we dare to add some redundant bit to form the code word and perform error correction at the receiver side. But this redundancy degrades the transmission rate. Transmission rate is k over n. And we would like to keep this transmission rate as high as possible while to reduce the decoding error as small as desired. But for this purpose, there is a strict bound of the allowed values of the transmission rate. So this is the channel capacity. And if the transmission rate is kept greater than the channel capacity, then the error-free transmission is definitely impossible. So this is the essence of the Shannon's theory. Now the capacity is simply given by this very beautiful formula, and it is determined by the noise power of the system, N, and the available signal power and bandwidth, P and W. Then we will be able to transmit this amount of bit faithfully per unit time if we apply appropriate coding. And quantum extension of this theory has been studied over a long time, and the issue is as follows. Given the channel transmittance theta, signal power P, and bandwidth W, then find the maximum transmission rate. Okay? And you can use all possible quantum operations at encoder and decoder and all kinds of quantum states. So this looks really general and difficult problem, but surprisingly, the solution was found by a group of MIT in 2004. So the maximum capacity of bosonic channel is simply given by this really beautiful formula using an entropic function G of X. Okay? So eta K is the channel transmittance for mode K, and K is a mean photon number for mode K. And we have some supremum of this quantity. And this theory also clarifies the optimal way of communication. So optimal encoding is made by coherent state modulation and separable encoding. So it's a really simple and classical technology. So the reason why this is optimal is simply because the coherent state is the annihilation, eigen state of this annihilation operator, and hence the best signal carrier for lossy channel. Quantum effect should be exploited at the decoding stage. So this is kind of a projection onto the superposition state of these separable coherent state code words. So it's sort of a large cat state. Such a projection can be translated into a kind of quantum information processing prior to the final measurement. And this is usually called a quantum corrective decoding. Now, today I'd like to use this formula to forecast the future communication performance. Okay, so this is the transmission rate as a function of the input power, launch power of the fiber input. Okay, and this circle is a recent experiment done by Arcato and Lucent for high capacity transmission. And this red curve is the near future optical communication. This performance is extrapolated from their results simply by expanding the bandwidth. Blue one is the quantum communication using a single fiber. So you can see that we can reduce the transmission power to attain a given level of transmission rate. And you can also increase the capacity by more than 300 times. But you can also see that we cannot exceed the 1 peta BPS level for a given 1 watt launch power. Actually, this 1 watt launch power is the fiber field threshold. If you input more power, then fiber may be melted down. So this is kind of a limit. And now you can also see this green line here at the top. So this is the communication performance using all electromagnetic field mode. So this is a very final bound of communication, and it's simply determined by only 3 parameters. Okay, channel transmittance eta, input power P, and Planck constant H. So nobody can go beyond this green line limit, no matter how much capacity you want. So quantum theory tells us that the communication capacity is finite for given finite power. The origin of this limit is simply that the Planck constant is very small but non-zero quantity. Okay, so this is the ultimate communication, and we can use this theory to simulate a deep space optical communication as well. It's a very long distance, and there is no amplifiers, and power feed is very limited. So it's a really quantum limited channel. Now, commonly used coding scheme is pulse position modulation coding, PPM. So let me compare several schemes. So this is a transmission rate in terms of the distance from the Earth. So this blue line is a PPM with a 1004 array format with an on-off detector right here. So we assume a 1 watt launch power from the satellite and 100 gigahertz rep rate. Okay? This blue line here, blue line is the limit of quantum decoder operating at the same 100 gigahertz rep rate. So you can see that this PPM almost saturates this quantum bound as the distance extends to Jupiter and Saturn. However, at the shorter distances around the Moon, then this coherent communication almost saturates this quantum bound. Okay? So we can make some design chart for future communications. So for free space link, the power budget is very limited. So we have to optimize the energy efficiency. So we concentrate the laser power on the very short time slot and encode the information by the pulse position and detect them by on-off detector. So this is almost optimal. So the channel type is Poissonian. The issue is how to shorten the time resolution. Now, for fiber, optical fiber, there is no serious power limit, and we have to optimize the spectral efficiency. So we use a multiple array quadrature amplitude modulation. It's a coherent modulation and detect them by homodyne detector. So the channel type is Gaussian. So this is the region around here, but in order to reach this ultimate bound, we may apply quantum receiver or quantum decoder, and the channel type becomes non-Gaussian. And the research direction toward this limit is still in preliminary phase. So quantum receiver is a new receiver to beat the bit error rate limit. And so we detect each optical pulse in a pulse-wise way, and we would like to minimize the bit error rate below the standard short noise limit. And this really works the experimental demonstration obtained by without any correction of losses. Now, quantum decoder, it is the ultimate receiver technology, and we have an important principle here. This is a super additive coding gain. Simply, which means when we double the transmission resources, such as by doubling the transmission power or the bandwidth, then the capacity can be more than double. And the capacity is usually defined by this ratio Cn over n at the n infinity. So this is the ultimate capacity. And this important principle was demonstrated by us 10 years ago using a polarization location coding with single photon. So this is just a proof of principle demonstration, and extension to this scheme to more practical coherent state is quite difficult and still open. Okay, so we come to the discussion on physical layer cryptography. Now, the QKD, in QKD, we make a very strong assumption. Eve is God, so Eve can do everything. And then the unconditional security can be beautifully proved. But I think this is too much for some applications. So we would like to make a reasonable compromise. Oh, good. So Eve is not God anymore. So, I mean, Eve's channel is worse than that of Bob. So the signal to noise ratio between Alice Eve is smaller than that of Alice Bob. Okay? So this is called the Wiretap channel. And we already know that for Wiretap channel, there exists a code that can transmit this amount of bits phase-free per unit time, making the leaked information to Eve arbitrarily small. Okay? So this is the provable security. And the theoretical framework was laid by Wiener for a long time ago, and soon later by Chizal and Kellner. Okay, so the capacity is the maximum rate of the reliable transmission, and to combat noise, we add redundancy and perform error correction. Secrecy capacity is the maximum rate with provable security. And this is determined by the difference between the two kinds of mutual information. Mutual information between Alice Bob and that between Alice Eve. And we have to introduce further randomness and perform privacy amplification. Okay? So let me describe these two schemes more intuitively. For capacity, we first set the transmission rate R smaller than that capacity. Then this rate and code length, this code length n, determines the transmissible message size n by this relation. And there must be a coding to transmit these messages faithfully to Bob. Okay? Now to achieve secrecy capacity, we have to extend the coding scheme into the two steps as follows. So we first encode a message to a code group, okay? Code group, say C2, and perform further randomization within the code group using this additional randomness. Okay? So this is to deceive Eve. So the message rate should be sacrificed to deceive Eve with this additional randomness. So in this sense, the reliability for Bob and security against Eve are in tradeoff relation, and we want to estimate the required resources for given level of reliability for Bob and the security against Eve. And redundancy and randomness should be minimal, but the capacity or secrecy capacity alone is not a sufficient measure. So let me mention this point for a while. So the capacity, okay, only gives the maximum achievable rate. So this is in the asymptotic limit. But a stronger characterization is given by the reliability function. Okay? So this is the exponent of the decoding error and defined for finite code length. So we can specify how rapid the decoding error decreases as a function of the code length. And for given reliability criteria, we can tell how long code length is required to achieve such given criteria. Okay? So this is a finite length analysis. And reliability function is defined by the Gallagher's theory, and this is determined by the channel matrix here. It's a channel matrix W, and the a priori probabilities here, and we have a transmission rate R, introducing some additional optimization parameter. So this is the reliability function. It's a concave function in terms of the transmission rate, and this point where reliability function becomes 0 is the channel capacity. And we can engineer any desired transmission rate with a known reliability function. Okay? So we'd like to extend this notion to the security characterization. Okay? So we introduce additional randomness here, and we had two kinds of rate. The rate RB for Bob, and another is the rate RE of the resolvability against Eve. So you see the new ones here, the resolvability. Okay? So this is actually the minimum size of randomness to deceive Eve. And this notion was originally introduced by Hahn and Verdu more than 20 years ago. So let me briefly mention what is the resolvability. So consider to input the random numbers to the channel to simulate Eve's probability distribution. Okay? So we have L of random numbers which are uniformly distributed. And an input U is sent through the channel. And let PU be output probability distribution for this input U at Eve's side. Okay? Then for any given target probability, pi n at Eve, if this Pn is identical to this target distribution pi, then messages U are statistically indistinguishable. Okay? Indistinguishable for Eve, observing this variable Z alone. And this means Eve can be deceived. And the resolvability is the minimum size of this input randomness. Okay? And we use this notion to quantify the security. And there are many kinds of metric. But maybe this statistical distance would be strongest quantity. So we use a Kalbach-Leibler distance between the output and target distribution at Eve, defined like this. And we'd like to make Bob's decoding error and Kalbach-Leibler distance against Eve as small as desired. So this is our trade-off program. And we introduce a notion of security function in our recent paper. So this is the dual function to the reliability function and corresponds to the exponent of the Kalbach-Leibler distance. And we can know how rapid the distance decreases at chord length n. Okay? So our recent result is the complete characterization of the trade-off between the reliability and security, and this can be done even under the cost constraint. So we impose some constraint on the input letters, such as energy constraint or bandwidth constraint, and we derive some trade-off curve of the reliability function and security function. Okay? So let me briefly explain some mathematics. So we have two channels. One is the main channel, WB, between Alice and Bob, and the other is the wiretap channel, WE, between Alice and Eve. And the reliability is measured by the Bob's decoding error with the reliability function. And the security is measured by the Kalbach-Leibler distance against Eve using this security function. Okay? And to define those functions, we introduce dual quantities phi of law here. So phi law is defined by the main channel, and phi minus law is defined for the wiretap channel. So this is also a dual relation. Then using this quantity phi, we can prove the following theorem. Now the decoding error and Kalbach-Leibler distance can be upper bounded in the form like this. And this f and h is the reliability function and security function defined by this sort of form. Okay, so we use a dual quantity here with the transmission rate and resolvability rate. And we have some optimization parameter rho and r. This is for power constraint. So the proof refer to this paper. And we show some numerical example. So here we show a reliability function for several cost constraints. So maybe gamma can be understood as the transmission power. So for larger transmission power, we can get larger reliability function, meaning larger reliability. And the horizontal axis is a sum of the rate of RB for Bob and RE for Eve. And we also plot the security function for the same transmission power. Then larger power means smaller security, I mean the weaker security. So we transmit more power, then Eve have higher possibility to tap the information from Bob, Alice Bob. Okay, so so this is a plot of these functions simultaneously, and the interval between these 2 points corresponds to the achievable secrecy capacity region, where the reliable transmission with a provable security is possible. Oh, important, yeah. Important classical error correction. This is, provable. Thank you. Wow, you're really carefully looking at slides. Okay. So let me show 2 examples of trade-off engineering. So we'd like to increase the security, keeping the reliability of Bob the same. Okay. So we increase the randomness part while decrease the message part, keeping the sum of these two quantities the same. Okay, then we can move from here to here in the security function curve while staying at the same level of reliability. So this change of the security function quantifies the increase of the security level. The other example is the security increase by channel concatenation. So we introduce further randomization with an auxiliary variable V. So this means we make another dice to shuffle 0 and 1 prior to the encoding with this X. Okay? By doing this, we can get another trade-off curve like these dotted lines. Okay? So we get the higher security function curve and lower reliability function curve. So the security is enhanced at the expense of the reliability. Okay? So this is an example. And we also derive a numerical result for practical wiretap channel. This is a Poisson wiretap channel. And it consists of a laser transmission in free space, and a photon counting. Okay? So this is a really transparent link in the large area. So Alice and Bob can tell if it's there, if it's in the channel. So what it should do is to hide from the legitimate users and correct scattered light to tap the channel. So if the channel is really worse than that of Alice Bob, so the degradation conditions are really met. And we can draw some examples of these reliability and security functions. And more importantly, we already know explicit code construction. This is a Wiener code. And this is the equal weighted code, and all the code words, okay, are in equal distances. And this code are shown to be secrecy capacity achieving as well, shown by Loren and Wagner. So our next work will be to implement this sort of free space laser link using the Wiener code. So now we are working on the 10-kilometer inter-building free space link between NICT and the University of Electrocommunications. So University Electrocommunications are right here. So this is Alice's site. It's a really small, okay, 10-kilometer distance. So we magnify the view. So now this is a telescope dome here, and Alice is in this dome, and Eve should hide right here or here and tap a scattered light. And this is the view of the experiment. This is a night view, and this red mark is a beacon beam. Okay, and this is a receiver side, and we can now detect the on and off signals at the 1 megahertz modulation. So this is a really preliminary step, and we would like to establish such a Poisson wiretap channel. Okay, so this is the summary. So we present a long-term stable operation of the QKD first generation and show quantum relay to extend the distance. And we also present our new theory of physical layer cryptography, especially the quantification by the reliability and security functions. So let me just remark 2 points. Now we are making a prototype of quantum photonic network, which will be completed in 2015. So this includes all kinds of QKD protocols, like BB84, DPS QKD, continuous variable QKD, entanglement QKD. And we also put photonic cipher called Y00. And then also add the free space link. It's a 10-kilometer free space link for physical layer cryptography. It's a Poisson channel. And these solid lines are now operating, and these dotted lines are now under construction. And very finally, I'd like to remark on a future study of quantum reliability and security. So our present result is still in classical framework. Okay? So channel matrix P of y by x is given, and we deal with the classical alphabet 0 and 1. But you already know that this channel matrix has deeper structure in the quantum layer. So this channel matrix is actually trace of the POVM and CP mapped quantum states. And this the given and fixed is this CP map quantum channel, and the input quantum state and POVM for outputs are variables, need to be optimized. And we also introduce Planck constant to this power constraint and derive a numerical characteristics of the physical layer cryptography. So such an extension is completely open and must be really fertile research field. Okay, so this is, thank you for your attention, and let's go as far as Photon will take us. Thank you very much.
Well, thank you very, very much. We have time for questions.
This Schrödinger state, that is very vulnerable to decoherence.
Yes.
Could you explain it again for how to avoid that decoherence?
Okay. Well, how to avoid is just to restrict the input to state. Yeah. If we want to teleport the arbitrary superposition, then there is no way. But if we restrict discrete set of coherent states, then those states can be noiselessly teleamplified, but it must be conditional way. We select certain detection event and filtered out unwanted decohered signals. And yeah.
Then can it be used for arbitrary superposition of states?
No.
So I see. Okay.
So it's only for application to relay or
certain
crash
restricted states.
Yes, that's right.
I see.
Any other question?
Yes. So another question about that nonlinear amplifier based extension that you showed. So my understanding is what you're doing there is that you're borrowing the secrecy proof for standard decoy state QKD, but you're saying that I'm only going to consider those instances when you successfully amplified it noiselessly and throw away rest of the data, and then that happens at certain rate. So your rate takes a hit, but you get larger distance, right? So my question is that I'm not so familiar with the security proofs, but I do remember that if you post-select, then there are some issues with the security proof, and it may have to be redone. So are you, in this case, are you just taking the secret key rates for the standard decoy state protocol, and you're just multiplying that by whatever probability of success of that nonlinear amplifier?
Well, firstly, we do not use any decoy state method. We rely on the coherent state implementation according to the low-end Prescale scheme.
I see.
And the security proof was given there, but we just, add some relay node and post-selection processing. But as you pointed out, there might, careful consideration should be given on the security proof, including additional post-selection. So maybe this might be my future, homework.
Just a minute. Could you go back to slide 55, please?
55, okay. This one?
Yeah. Can the lights be turned down, please? Thank you. I was just a bit surprised here to notice that. Yeah. To see that you propose to use optical fiber beyond the moon. What did you mean?
Oh, no, it's not I see. Right, yeah. We cannot,
pretty long fiber.
Yeah, we cannot install the fiber up to moon. It's a really challenging frontier.
Yeah. It's way beyond the moon, actually.
This means just free space coherent communications, and local oscillators should be prepared on the Earth, and lasers are transmitted from moon, and we have to transmit some coherent information.
Thank you.
Good point.
Thank you. Simon, you had a question? But before that, could the next speaker come and set up so they can start the next talk on time, please? The next speaker could just set up. And Simon, your question?
It's my understanding, to my understanding, the expectation that for general bosonic Gaussian channels, coherent states from the optimal coding scheme is only a conjecture. Even though for some Gaussian channels, probably for the kind of thing you are using, this may actually be probably optimal.
Yeah, we
Now,
could.
now my question is, if this conjecture is proved for general bosonic Gaussian channels, will it make any difference to your plan of things for the future?
Yeah,
will it
right.
make any difference to your plan of things for the future?
Yeah. Well, I don't know how to exclude the possibility that other kind of states than coherent state could not be optimal solution, but maybe another kind of state can also be optimal. But at least coherent state encoding can achieve the maximum rate. But we could not exclude the other possibility that, such as photon or squeeze state can also achieve the coherent state, the bosonic capacity. So, this is the answer to the question.
Any further question? Well, if not, let's thank the speaker. Oops. Yes, no? All right. You want to ask a question? No? All right. Sorry. So, so again, let's really thank the speaker again.
Yeah, thank you.
And it's my pleasure for the last time to offer this shawl to show our appreciation to our speaker.